Okay, yesterday we start to find out a solution for making compatible the switching action of the hard switching commutation in presence of an ohmic inductive load. Okay, the solution is reported here in this page. You can see that there is the supply here, which should be connected to the inductive ohmic load represented by the series of the inductor L and the resistor R by means of that specific combination of switches SWA plus and A minus that works in a complementary way. So there is no possibility to have both conducting or both, say, left open. When A plus is on, A minus is off, and vice versa is also true. In order to make this commutation unit resolution function Q is connected to the commanding port of the switches, okay, in this way, okay, and the behavior can be also represented in an alternative way, which is that in which the two switches are replaced by a bipositional switch commanded by the same unitary switching function Q. Just to give you some, say, name of these components, the switch that make possible the connection between the energy source E and the load is called the main source. Sorry, the main switch. Okay, so this A plus is the main switch connecting the source to the load. Then we have A minus, which is the free wheeling switch. It is the switch that is in charge to provide a recirculating path for the inductor current when the main switch is left open. Okay. I named this node as A, okay, and the common node as N, just as a few indications that will be useful later on, is that you can see the node A, this node is the common node between the two switches, okay, and we have, let's say here, the inductor currents. So the behavior of what is connected to the node A is to have the current as constant as it possible, because the inductor, as you well know, dynamically acts as a current source. Okay, it tries whatever it takes in order to maintain the current to be, say, constant. Okay, so the behavior here is to have something, let's say, acting as a current source. Okay, here. If you look at the these two nodes here, okay, so the nodes that I call N and the opposite node of the switch A plus with respect to A. So if you can see that the characteristic of the voltage here is to become almost constant. Okay, here the battery is constant, and so the behavior here is that here the electrical characteristic acts as a voltage source. Okay, so the current exiting node A as the characteristic to become, say, almost constant, okay, because there is an inductance, so there is no instantaneous variation of the currents. The voltage across the let's say the source connected, or the nodes on the left side of this combination of the switch becomes, say, a voltage source, so the constant voltage. Okay, so this is what we can do in order to make compatible the forced commutation with inductive ohmic load. But what happens if we have the capacitive ohmic load? Okay, so capacitive ohmic load. Let me redraw the circuit that we already analyzed. Okay, this circuit has the problem that when you close the switch, you are forcing the voltage across the capacitor, let me call it VC, to become equal to E. Okay, and this is something that induces large power dissipation. Okay, for example, it induces overcurrent flow into the switch, and this happens to become a very dangerous situation. Okay, inducing possibly also permanent failures, etc. Okay, so it's something that we have to avoid. This situation here is the dual of that you found out for the ohmic inductive load. Okay, so we are trying to modify the topology of the circuits in order to power up a capacity of load with a forced commutation switch without inducing the large overcurrent stresses in the main switch. Look at these circuits, okay? And if you look at these circuits, and if you try to use the same strategies that we applied for the ohmic inductive load, so we change the topology of the switches. For example, we can add a switch in order to solve the problem. But in that specific situation, there is no possibility to add another switch in order to solve the problem as we did for the capacitor or the ohmic inductive load. In effect, any position you can test for another switch acting in a complementary way with the main switch here does not solve the problem. Okay, try to put, let's say, a switch, for example, here, but this is something that is not solve the problem. Try to put a switch over here. There is no possibility to solve the problem. Without any kind of position you are testing here is not useful for solving this problem. So here we have to change the kind of source we are applying to energize the capacitive ohmic load. The problem here is in this source here. A possibility is to change from voltage source to current source. So let's try to have the current source. So we have a current source here, supposing that the current is I. Okay, we have the same main switch here, capacitor and resistor. So what happened? This is the switch. If I want to charge the capacitor, so if we want to, say, energize it to provide energy, then I can close the switch. Okay. When I try to, say, interrupt the flow of energy from the source to the capacity of the load, I can open the switch. Okay. So these circuits has a main problem. Okay, because what is the voltage V across the switch? We know that we have a voltage VC across the capacitor, but we don't know, because it cannot be defined, which is the voltage across the, say, the current source. So having this kind of circuits leads to what is called a degenerate circuit. It's not possible to define the voltage V across the switch. Okay, so this circuit is, say, a bad circuit. Okay, it doesn't work at all. So let's continue to use the current source, but put a switch in parallel here. Intake the same load as before. Okay. Now what happens? If I want to energize the circuit, okay, I have to say open the switch, okay, making possible for the current I to flow charge in the capacitors. When I want to discharge the load, the only thing that I can do with the circuit is to close the switch. But when I close the switch, what happens? That I force the voltage VC to become zero. And this, again, is a situation that leads to, let's say, overcurrent flowing into the switch, okay? Basically, all the current flowing in the generator I flow here, okay, is a situation that leads to malfunction. It's not a situation that leads to dissipative switching, exactly in the same way we have, say, basically in the original circuit with the voltage source E. So now we can act on these circuits to modify a little bit the topology in order to solve the problem we can have with these circuits. Okay, this is now it's possible. For example, you can add another switch here. Okay, and the switch, the red one, acts exactly in a complementary way with the other switch. Let me call this switch A plus, and this is the A minus switch. For example, when I want to energize the circuit, I have to open the switch, I have to close this one, and I am connecting the source of the current I to the load. Okay. When I want to de-energize the circuit, I want to interrupt providing energy to the capacitor, then I have to close the switch here, and I have to open this one. A plus will be open. In that case, what happens to the load? The load, see, is, let's say, left independent from the source. It is a CR load that can, say, discharge the voltage with a time constant C multiplied R. The current flowing here is clamped, say, by the value of the source he, is no more a problem. The voltage across this A plus source is negative VC. Okay, so in order to make it compatible, the switching action of the main switch connecting the power source to a capacitive load, we first had to change the nature of the source of the energy. From a voltage source, we change into a current source, okay? And then from the current source, we modify the topology of the switch, again adding a second switch with a, say, complementary action in order to, say, make compatible this switch action. Okay, so at the end we can say that for capacitive ohmic load, the solution is this one. Current source, let me call this node A and the common node N. This is the switch A plus, this is the switch A minus, and then here we have the load. Okay, again we see that the same structure that I employed before with the ohmic inductive load now is employed here for the capacitive ohmic load. Okay, so the combination of the switch that has a common node here operating in, say, complementary way. they are commanded by the unitary switching function Q. And since they are connected to the switch, which is called A, plus or minus, that we can call the unitary switching function as QA, for example, in order to have Q and Q naught here, making possible to have both switches, say, on simultaneously or both off. When one switch is on, the other one will be off. And these circuits can be also regarded as a circuit in which you have a p-positional switch. Like this. And see, R. Okay, you have the node A, and the switch is commanded by the unitary switching function that now we call QA. Okay. Some comments on these circuits. Look at the node A here. The node A, which is the common node between the A plus and minus switch, is connected to a current source. So here you have again a current source connected here. So the current is provided in a constant way. If you look at the node on the left side of this switch topology, so the nodes that are across the capacitors, so you remember that dynamically the capacitors act as a voltage source, trying whatever it takes in order to maintain constant voltage across it. So what happens here, that is acts exactly as a voltage source. The main switch now is this switch here. Okay, is the switch making possible the connection between the source and the load, and this is the freewheeling switch, main and freewheeling. Okay, so we solved the problem for the ohmic inductive load, capacity ohmic load. Just say to complete the discussion, is there a possibility to connect a current source to a ohmic inductive load? Okay, we know that the switch should be connected here. Okay, just to complete the combination between the current and voltage source E and I to the ohmic inductive and capacitive ohmic load. What happens here? If you have the switch, let's say, left open, then we provide the current I to the load. Okay, but when I close the switch, okay, what happens that the current I is forced to circulate in this path, but what happens that, and this is possible, okay, but when you open the switch again, okay, if the current IL is the same as I, there is no problem. But typically, in general, the current I will be different from the current IL from the previous phase, so you induce again, say, dissipation in the switch, etc. Okay, so this is a dissipative phase. Okay, is there the possibility to add the switch in some position to solve this problem? No. Try by your own, for example, by adding a switch here, okay, and the same situation happens as before. So again, this circuit is not useful. Okay, so the only two possibilities to connect a power source to a reactive load, ohmic or capacitive load, is when the source and the load have different reactive nature. So let me put in words, okay? A source can be connected by a hard switching operated switch to a reactive load without any issue, only if the source and the load have opposite reactive nature. What does it mean, opposite reactive nature? Opposite reactive nature means, for example, look at this capacity ohmic load, that what is the reactive nature of the capacitive load? Is, let's say, that of a capacitor. So to maintain the voltage as constant as it possible. So the reactive nature here that of a voltage source. And the load here is current source. As you can see, I am able to solve the hard switching connection. I make compatible this combination because the source and the load have opposite reactive nature. Current source, voltage source. Okay? See what happens in the ohmic inductive load. Here, what is the reactive nature of the load? The reactive nature is that of an inductor. So to maintain as constant as it possible the current flowing through it. So is like a current source. Okay. And what is the reactive nature of a voltage source? To maintain the voltage constant. So it is a voltage source. Again, we solved the problem of the compatibility of the switching action between a source and the load because the reactive nature of the source and the load are opposite, voltage and current. Okay? So we can say derive a common result, common solution to this say discussion. The topology that is useful to say connect a voltage source and a load, reactive load, by say using switches that are forced in their commutation, is to use what is called the switching power pole. The switching power pole is exactly this combination of the switch. Let me put it this way. Okay, I just simply modify the position of the switch A plus. This is the node A and this is the node A. Okay, this is our switching power pole. Is made by two switches basically that acts in a complementary way. So that means that we have two switching function that are one the logical negation, logical not of the other one, so QA. So we have QA not here and QA here, commanding the switches to be, say, not simultaneously on or off, but when one is on, the other one is off. At the node A, the behavior should be that of a current source, and this can be forced by including here an inductor. The inductor, dynamically, the reactive nature is exactly that of a current source. Okay, the current IA is basically, say, considered to be constant. Okay, so there are no large variation. The behavior of the voltage across the input node of this switching power pole is that of a voltage source. And so we can stress this fact by considering connecting a capacitor at the input side. Let me call this CD. Okay, so we have one input port and one output port of these switches. Okay, here you have a constant voltage, and so this is called also the voltage port. At the exit, the opposite side, we have a constant current, so this is also called the current port. So we have current port here, voltage port here. A plus is the main switch. A minus is the freewheeling switch. Remember that the unit resolution function QA is such that when QA is 1, A plus is on, and A minus is off. When it's 0, A plus is off, and A minus is on. Okay. In this discussion, the switches are always supposed to be ideal, both statically and dynamically. Okay, they have no problems. They close instantaneously. They have no losses, etc. Okay, because we are trying to focus their attention on the behavior, on the circuit, on the impact of this structure, and not just on the second order problems and issues. Okay, so this is the switching power pole that we learn to be the standard structure that is say, can be employed to connect the input source with a reactive load. Let me just discuss with you some example of application of this switching power pole, which is the basic structure that you can find anytime in a power circuit. Okay, so let's start with an example. Example number 1. Suppose that I have a load, a generic load, connected to the current port. So let me draw here the switching power pole. A plus, A minus, input capacitor CD, This is the node N, the common node. This is the current port. Okay, so I have a load connected to the current port. Okay, generic load. There is no the difference in my discussion, but just to make situation a little bit more interesting, supposing that the load is a ohmic resistive load. Sorry, ohmic capacitive load. This is my load. Okay. Okay, as you can see here, I am connecting this capacitive ohmic load to the current port. So this means that I have here the source E. Also remember that here you have the switching, the unitary switching function. Okay, just to complete the scheme. Okay, I have here the unitary switching function QA that commands these switches. Okay, so look what happens to the voltage here. This is the voltage VAN. VAN is the switches are ideal, so when they are closed are ideal, let's say short circuit. When they are open, they are fully open circuit without any current flow into it. So when QA is 1, it means that the A plus switch is on and A minus is off. Okay, so VAN is basically the same of E. When QA is null, the opposite happens. So I have A plus is open, A minus is closed, and so this is 0. So we can say that VAN T is E that multiplies QA. Okay. At the same time, supposing that the unitary switching function QA is a periodic waveform. So if you look at the time waveform of the unit switching function, you can see that you have something like this. Okay, 0 to 1. So here is, say, 1, so it means that A plus is closed. When it is 0 is A minus, which is closed, etc. This behavior is periodic, and the period is, let's say, TS, so the switching period. This is the time interval in which the unitary switching function is on. So when the top switch is on, let me call it T on, okay, which is the average value of this unitary switching function. QA average value is 1 over TS of QA plus, QA T in the T. So 1 over TS. Of course, this is QA is just not null over T on, okay? And so it is T on over TS. This is QA average value. But we also we already defined this quantity T on over Ts. This is defined as the duty cycle. We call this the duty cycle of the switch SA. Okay, so the average value of the unitary switching function is exactly the duty cycle T on over Ts, so the ratio between the time interval in which the A plus switch is on respect to the switching period. Okay, so if you consider the time waveform of the voltage VAN, you can see that when you are in the T on interval, this is E. When A minus is on, this voltage is null. Okay, so this is T on and this is Ts, which is the average value of the voltage VAN. But VAN average value is 1 over Ts integral extended over the period of the voltage VAN T, the T. This voltage is not null just during T on, and the value is E, so we have E T on over Ts. So we have E multiplied the duty cycle dA, which is the ratio. Okay, this is the average voltage that you have at the nodes VAN. Okay, so is the average voltage you have between these two nodes here. What about the voltage VO or V naught at the output? But if you consider that the combination of LC exactly in the way I drawn in the schematic is that of a second order low pass filter, okay, it's easy to understand that this low pass filter can be designed just to filter out all the high order harmonics and just to maintain the DC fundamental component. Okay, so at the output VO V naught can be exactly the DC component of the voltage VIN, which is the average value. So this is A multiply the duty cycle. We have the expression of the output voltage V naught of the circuits, and we have the expression of the, let's say, the instantaneous value. Okay, so compare this equation here, which is the instantaneous value of the voltage VIN, with the instantaneous value, the average value of VIN, which is this one. Instantaneous expression of the voltage VIN is like E that multiplies QA. Average expression is VIN E multiplied the duty cycle. You can see that there is a similarity in this expression, because it seems that I can pass from instantaneous expression to the average expression simply by replacing instantaneous value with their average value. Okay, I replace the instantaneous value of VIN with its average value, E is instantaneous and it's the same of the average value because it is a constant. And then I replace the unit switching function with its average value, which is the duty cycle. Okay, this is quite common in power electronics, so it's easy to see the direct transposition of an instantaneous expression into its average expression, just taking the same, say, the same shape of the expression with all the time variable quantity replaced by their average value. Okay, basically this is possible anytime you have this kind of relationship. Suppose that you have this very generic expression, instantaneous expression, in which we have two variables, the y variables and the x variable, and q, which is the unitary switching function. Okay, suppose that the period is t of this function. Then you can pass from this expression to a, say, average expression, like for example this one, x multiplied the duty cycle. Okay, this is the average expression, this is the instantaneous expression, if and all if there are specific conditions. Okay, the conditions are that the average value of x over the period t of the unitary switching function is the same of the average of the variable x just over the interval in which you have t on, basically, okay, when the unit switching function is 1. And it is the same of the average value of the x variable during the time interval in which the unitary switching function is null. If x is equal to xd is equal to x1 minus d, if this condition holds, then this is true. You have to take the average of the variable x that multiplies the unit switching function during the whole period, the average value during the time interval t on, and the average value of the variable x during the time interval between t on and t, basically. If these average values are the same between them, of course, this happens. Okay, here in this expression, which is the function x that multiplies the unit switching function, is a constant e. And then when you have a constant value multiplying the unit switching function, is obvious that this condition holds, because the average value during t, ts in this case, is the same of the average value during t on, and it's the same of the average value during ts minus t on. Okay, so for a constant quantity multiplying the unit switching function, this, let's say, transposition, this direct characteristic is always true. Okay. We employed what we learned, so we employed the existence of this, say, switching power pole for that specific case, just an example, and we derived a specific DC to DC converter. Most of you recognize that this circuit is, as a name, DC-DC converter is also known as step down or buck converter. Okay. Let me just consider this current here, which is IA, okay, and then consider the current flowing here. This is the current flowing to the switch A plus. Let me call this ID, okay, of the switch A, which is the relationship between IDA, so the current flowing here, and the current IA. Let me just do IDA will be equal to IA when the unitary switching function is 1. Okay, because when the QA is 1, A plus is closed. And so when A plus is closed, when the switch is closed, okay, the current flowing into the ID branch is the same of the current flowing here. Okay, no current can flow here because the switch A minus is open. When the QA is null, A plus is open, so no current can flow through this switch, so IDA is 0. So we can say that IDA instantaneous expression is exactly IA multiplying by QA over T. Now my question is that I have this instantaneous expression, okay? Let me put this into the average form. So suppose that I can translate this into average expression. So it means that I have IA average value multiplied the average value of the unit switching function is the duty cycle. Is this true? So I can express exactly I did for the voltage the average value of the current IDA. But the problem is that I have to consider the behavior of the function multiplying the unitary switching QA. Okay, so I have to consider the behavior of this quantity here. According to my previous, say, description here, okay, depends on the function multiplying the unitary switching. I have to verify that for each portion in the period t on, or say t minus t on, the average value of the variable x is the same. So I have to consider which is the behavior of the current IA. So let me just put again my back circuit. Okay, I'm interested in this current, the behavior of this current IA. Let me just sketch how this current behaves. Okay, supposing that we are in the steady state situation, so it means that we have no transient at all. Ts is my period. Okay, so if you are in the steady state situation, the current you have at the beginning of the cycle will be the same current you have at the end of the cycle. Okay, if it is not true, that means that cycle by cycle you have a variation of the current, so you are in a situation which is no more stationary. You are not in steady state. So the behavior is, let's say, having a current, for example, started from here. Let me call this IA1. Then what happens during the time interval t on? Remember that here the QA is 1. So it means that this switch is closed. Okay, this is open. So the circuit is here. The voltage that you can have across the inductor VL is the voltage you have here, which is E minus watt, which is the voltage that you can have here. The voltage you have here is the, let's say, V A N average value. Okay, because this is the same voltage you can have at the output. VO, which is VN average value. We learned, say, in the previous analysis, okay, that the output voltage when the filter is designed to filter out all the high order harmonic except for the DC value is exactly the average value of VAN. This is E minus VAN average value is the duty cycle multiplied E. So this is E1 minus the duty cycle. Okay, the duty cycle ranges from 0 to 1, so this quantity is positive, meaning that the current flowing to the inductor rise up. Okay, remember that VL is L the IL over the T. Okay, so the voltage VL is exactly E1 minus the duty cycle, so it is positive, so the slope of the current will be E1 minus dA over L. This is a positive slope, the current rise up. Okay. Then in the second interval, then QA is 0, it's meaning that this switch is A plus is off, A minus is on, so the voltage here is 0. VL becomes here, VL in this phase is negative VAN average value, so negative dA multiplied E. Now the voltage across the inductor is negative, so it means that the current decreases. Okay, the slope here is negative dA E over L, the slope, okay, etc. So my current IA, supposing that we are starting with a positive current, ranges from IA1 to IA2, having this ripple, okay? It's not a constant current, okay? But basically, if the inductor L is very large, this ripple can be quite small, so we can consider that effectively the current flowing exiting the node A, the common node, is basically, say, replying this behavior of a current, of a constant current source. Okay, so now we have to verify that the average value of the current IA during the period Ts, during the period T on, and during this interval here is the same. Okay, in order to consider the possibility to translate instantaneous expression into similar shape, similar form of the average value. Let me compute the average value of IA over Ts. This is IL over Ts, which is 1 over Ts, yeah, T. Simply, you have to consider that this average value is the, let's say, the area, okay, of this the area of this, say, shape, this geometrical shape, divided by Ts. Okay, so we can split this in a rectangular area here, plus a triangle. Okay, if you do this, it's very simple to derive this equation, but you can solve it in any way. It's very, say, simple integral. Okay, so the rectangle has area which is IL1, which is the 8, and Ts, which is the base, plus the area of the triangle, which is Ts, IL, this is IA, sorry. IA2, IA1 divided by 2. Base 8 divided by 2. Okay, so you can find that this is IA1 plus IA2 divided by 2. So the average value of the current is exactly something which is here. Okay, this is IA average value over Ts. Now try to compute the average value over Ton. Ton is the time interval, is a portion of the total Ts period, in which Qa is 1. Okay, this is also given by dA multiplied by Ts. Okay, so IA average value over dA multiplied Ts is 1 over Ts, the integral over Ton of the current IA multiplied by T. This is 1 over dA Ts. Again, we have the average value just of this, say, portion, so this quantity here. And you can find this quantity simply by IA1 plus IA2 is a trapezoid, so it is not difficult to find out the area. And so you can see that this is IA1 plus IA2 over 2, which is the same as before. And then the final computation is the average value over Ts minus Ton, which is also 1 minus dA multiplied Ts. Again, is the area of another trapezoid. Trapezoidal waveform now is this part here. So I have to multiply IL1 plus IA2 multiplied 1 minus dA Ts divided by 2. So it is Okay, again, I can simplify these two, and the result is this one, which is the same as before. So I verified that the average value of the quantity of the variable instantaneous variation of the function that multiplies the unit switching function has the same average value over Ts over T on and over Ts minus T on. So this direct transposition between the instantaneous expression and the average expression is true. Yes. Okay, so, and this is just a proof that when you have to do with constant function, just the E function in the previous expression here, okay, or with triangular waveform, so piecewise combination of waveform, this transposition between instantaneous expression and average expression typically is working, and this is always the case for power application. Okay, so you can consider this direct transposition to be most of the time to be correct. This is just was an example leading to the buck converter using the switch power pole. Let me show you an example that we name number 2, okay, in which I have a load connected to the voltage port. Okay, in the previous example, number 1, the load was connected to the current port. Now I have my switching power pole, A plus, A minus, node A, okay, this is my switching power pole. Let me call this CD. Okay, the switching power pole is here. Now my load is connected to the voltage port. So the load is connected here. Load. Okay, let me call the voltage across the load as VD. Okay, and here you can connect at the current port a source, supposing that the source is, let's say, a battery. Now the circuit is this one. Let me just to consider this is the node N. The instantaneous expression of the voltage VAN over T is basically is VD multiplied by QA. Okay, depending on the instantaneous value of the unitary switching function, QA plus QA can be 1 or 0. When a QA is 1, A plus is on, so meaning that VAN is the same as VD. When A plus is off, A minus is on, VAN is null. So the instantaneous expression is exactly this one. Direct transposition to the average expression says that this is VD. Okay, my hypothesis here is that VD is constant across the load. Okay, and so that means that you have dA. Okay, now instead of considering the duty cycle dA, okay, let me just considering the complementary duty cycle. What I intend to do. QA is the unit switching function of the switching power pole. Okay, so QA basically is the unit switching function of the switch A plus. When QA is 1, okay, it means that A plus is closed. Okay, when QA is null, it means that A plus is, let's say, is open, okay, is left open. So this is the same of the unity switching function of the QA plus, but this is nothing new, because if you look at the oh my god, where is here, okay, QA, which is the total unity switching function which is supplied to both the switches, is exactly inalterated the function QA commanding the switch A plus. Okay, but if you look at the unity switching function commanding the switch A minus, this is the complementary function. Say QA not is 1 minus QA, okay, because you need to act in a complementary way. So that means that if you consider the duty cycle dA, the duty cycle dA is, as considered up to now, is here. The duty cycle dA is the average value of the unitary switching function QA. If you consider not QA but 1 minus QA, this is QA. That can be periodic, that can be similar to that we previously considered. Okay, 1, 0, 0, T on, etc. The average value is TA. If you consider QA not, which is 1 minus QA, so the unitary switching function of the low side switch, this is something like this. Okay, and which is the duty cycle of this. The duty cycle is, let me call 1 minus dA. The average value of this quantity is exactly 1 minus dA. So if you consider this expression as VD of 1 minus QA not, okay, because QA not is 1 minus QA, so you can always put in this form. This also is VD 1 minus dA. Let me call this dA minus if you want. It's not the same dA, okay? I don't want to put dA not, because dA is not a logical function, okay? dA of the switch A minus. If you put in this way, we are just considering that our switch we are commanding is no more this one. The basic switch that I'd like to command is the low side switch in this circuit, okay? This is useful because VAN average value, so the average value that you can have here, this value here, in steady state condition is also equal to VG. You know that VAN as a function of t will be VL plus VG, which is a constant. But in steady state condition, the average value across VL is null. In steady state, VL average value is null. remember our previous discussion of the current flow into the inductor. In a steady state, I said that since you have no more transient, the current at the beginning of the cycle should be the same current at the end of the cycle. EA1 is the same of the current flow into an inductor, okay? So this is always say, true. And remember that VL is L day L over the T. So that means that IL at the end of the cycle minus IL at the beginning of the cycle would be something like 1 over L, 1 over Ts VL T in the T, okay? Inverting this equation. But since ILTS minus IL0 is null in steady state, okay, it means that this integral is null. So in steady state, the integral 1 over Ts VL T in the T is null, okay, for this condition. But if this integral is null, the average value of VL, which is 1 over Ts integral of VL T in the T, will be also null, because this integral here, according to this fact, is null. So in steady state, the voltage across the inductor is null. So we can say the average value of the voltage VIN, since the average value of the voltage across the inductor is null, is the same of Vg. So we can say that, applying here this consideration, that the voltage Vg at the, say, which is our input source here, is Vd multiplies 1 minus the duty cycle of the low side switch. So if you want to derive Vd, you can use this final expression to extract Vd. Vd is Vg over 1 minus dA minus. People who attended power electronic course can recognize in this expression the expression of a DC to DC converter, which is known as the step up or the boost. Since DIA is ranging from 0 to 1, okay, it means that the voltage VD is larger than the voltage VG. It's a kind of DC-DC converter, so a power converter that converts a voltage VG into a higher voltage VD across the output. Okay, this is just an example, of course, of application of the switching power pole. Just to indicate that the structure that we find out with the trying to solve the problem of the dissipative switching action in connecting a reactive load is the basic structure, the switching power pole, that will be used in any kind of power converter. Okay, you can find the same structure into, let's say, a more complicated, for example, DC-DC converter, for example, also in an isolated converter, in the buck boost, etc., etc. Okay, so the switching power pole, this is the main building block of power switching converters. In converter, say, made up by switching action composed by switches and reactive elements, including the most employed topologies that some of you already knows. Okay, and we, starting from this basic knowledge, then we use the switching power pole for deriving, let's say, bidirectional converters that are currently employed to drive electromechanical actuator. Okay, so have you any questions about this kind of derivation or the examples? something which is not too clear for you, that requires more explanations. Okay, think about these. Maybe you can ask me later. Okay, if you have no questions, I can interrupt here this lecture. I'd like to thank you for your attention. Have a nice day, nice weekend. See you next Tuesday at 10 a.m. Okay.